A silent rule controls everything, from the way light bends around a star, to the way your heart keeps its rhythm, from the motion of distant galaxies, to the tiny dance of particles inside an atom. That rule is not written in stone, it is not carved into space, it is written in mathematics. Numbers describe the orbit of planets with shocking accuracy. Equations predict the existence of particles before anyone builds a machine powerful enough to see them. Long before telescopes detected gravitational waves in 2015, the math already knew they were there. Long before Neptune was seen through a telescope in 1846, its position was calculated with nothing but equations. Think about that carefully. A human writes symbols on paper, and years later the universe confirms those symbols are correct. Why does math work? Why should symbols invented by the human mind match the behavior of stars billions of light years away? The universe runs on numbers. Galaxies move in equations. Atoms follow formulas. The expansion of space can be written in a line of mathematics. The bending of time can be captured in a tensor equation. Even chaos follows precise laws. But why? Is the universe made of math? Or did humans invent a tool that just happens to fit reality perfectly? The mystery goes deeper than most people realize. In 1960, physicist Eugene Wigner wrote about what he called the unreasonable effectiveness of mathematics in the natural sciences. He was not being poetic, he was confused, he was pointing to a real puzzle. Mathematics often predicts things that no one was looking for. Paul Dirac's equation predicted antimatter before anyone knew it existed. Maxwell's equations predicted radio waves before technology could detect them. Einstein's equations predicted black holes before telescopes could confirm them. The math seems to know secrets about the universe before we do. That feels almost impossible. Math is abstract. It lives in the mind. It is built from logic and symbols, yet the physical world obeys it with extreme precision. The value of pi appears in circles everywhere in the universe. The same constants appear in distant galaxies as they do on Earth. The same equations describe falling apples and orbiting moons. The deeper scientists look, the more mathematical reality becomes. Modern physics is not written in simple numbers. It is written in complex structures like Hilbert spaces, group symmetries, and curved space-time geometry. Reality at its core seems less like solid matter and more like information arranged in patterns. Some physicists now argue that physical particles are not objects at all, but excitations of underlying mathematical fields. That means what we call reality may be a structure of relationships defined by equations. This raises a disturbing possibility. Maybe math is not just a language we use to describe the universe. Maybe math is the universe. But there is another side to the story. Some thinkers argue that we shaped mathematics to match what we observe. We created numbers to count objects. We developed geometry to measure land. We refined algebra to solve practical problems. Of course, math fits reality because reality inspired it. In that view, math works because it was built from experience. Yet that explanation struggles to answer one key question. Why does pure mathematics, developed with no physical goal in mind, later describe nature with perfect accuracy? Non-Euclidean geometry was once a purely abstract idea. Decades later, it became the foundation of general relativity and the theory of curved spacetime. Complex numbers were once dismissed as imaginary. Today they are essential to quantum mechanics. The pattern repeats again and again. The human mind discovers a mathematical structure, and later the universe reveals that same structure in its deepest laws. This video explores that mystery step by step. You will learn why scientists trust mathematics more than intuition. You will see how equations predicted entire worlds before telescopes confirmed them. You will understand the difference between inventing math and discovering math. You will explore three powerful explanations for why mathematics fits reality so perfectly. And you will hear the perspective of physicists like Richard Feynman, who argued that nature does not obey math, but simply behaves in consistent ways, while math is our best description of those patterns. By the end, you will see that this question is not just about science. It touches philosophy, logic, and the limits of human understanding. If math is only a tool, then the mystery is about pattern and order. If math is discovered rather than invented, then mathematical truths exist outside human minds. If reality itself is mathematical, then every star, every particle, and even your thoughts may be part of a vast equation. That idea changes how we see existence. This is not just a scientific puzzle, it is one of the deepest questions ever asked. The answer may reshape how you think about reality itself. Stay with this video until the end, because the final explanation challenges the way most people think about the universe and about mathematics. The conclusion is not simple, it is not comfortable, but it is powerful. Welcome to our channel, where we explore the biggest questions in science and reality with clarity and depth. If you enjoy deep ideas explained in simple language, subscribe now and join us as we uncover the hidden logic of the universe. Mathematics does something that almost no other human creation can do. It predicts reality before reality reveals itself. It reaches into the unknown and returns with answers that later turn out to be true. This is not exaggeration. It has happened again and again in the history of science. In the early 1800s, astronomers noticed that the planet Uranus was not moving exactly the way Newton's laws said it should. Its orbit had small irregularities, tiny deviations. Instead of assuming Newton was wrong, two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, trusted the equations. They believed something unseen was pulling on Uranus. Using only mathematics, Le Verrier calculated where this hidden planet must be. He sent his calculations to an observatory in Berlin. On the very first night they looked, there it was, Neptune, a planet discovered not by looking at the sky, but by solving an equation. The math pointed to a location in space, and the telescope confirmed it. It was as if the universe had been hiding a secret, and mathematics forced it to confess. That was not an isolated event. Decades later, James Clerk Maxwell wrote down 4 equations that described electricity and magnetism. At the time, scientists studied electric charges and magnetic fields as separate phenomena. Maxwell unified them into one mathematical system. When he solved his equations, something unexpected appeared. The equations predicted waves traveling through space at the speed of light. Maxwell realized those waves were light itself, but the math also allowed for waves with different frequencies, invisible to the human eye. Radio waves. No one had detected them. No one had built a device to generate them. Yet the equations demanded their existence. Years later, Heinrich Hertz produced and detected radio waves in a laboratory, confirming Maxwell's prediction. Again, mathematics spoke first. Reality followed. The pattern continued into the 20th century. In 1915, Albert Einstein presented his theory of general relativity. The equations were complex and abstract. They described gravity not as a force, but as the curvature of space-time itself. When Einstein explored the consequences of his equations, he found something strange. They predicted ripples in space-time, waves that would travel across the universe when massive objects accelerated. These waves would stretch and compress space itself. Einstein was not sure they were real. For decades they remained a mathematical possibility. Then in 2015, the LIGO experiment detected gravitational waves from 2 colliding black holes over 1 billion light-years away. The signal matched Einstein's equations perfectly. The math had been waiting for a century. It was correct all along. This is not normal. In everyday life, tools respond to reality. A hammer drives a nail because we physically apply force. A thermometer measures temperature because it reacts to heat. But mathematics does not physically interact with the universe. It exists as symbols, logic, and relationships in the human mind. Yet those abstract symbols consistently describe physical reality with extreme precision. The orbit of Mercury, the spectrum of hydrogen, the expansion of the universe, the behavior of subatomic particles, all fall into line with mathematical structure. Even more surprising, some equations seem too beautiful to be accidental. They are simple, symmetric, and elegant. Physicists often talk about beauty as a guide to truth. Paul Dirac once said that the laws of nature should be expressed in beautiful equations. That belief led him to write an equation that combined quantum mechanics and special relativity. The equation predicted the existence of antimatter. At the time, no one had observed such a thing. Soon after, the positron was discovered. The equation was right. Again, it begins to feel almost magical. Mathematics seems to know things before we do. It feels as if the universe is written in a hidden code, and mathematicians slowly decode it, piece by piece. But magic is not an explanation. So what is going on? One possible answer is simple and grounded. The universe does not obey mathematics. It behaves in patterns. Those patterns exist whether we describe them or not. Apples fall at a steady rate. Planets trace consistent paths. Light bends in predictable ways. When patterns repeat, the human mind searches for structure. Mathematics is the most precise system we have for describing structure. In this view, math is a language, a powerful language, a precise language, but still just a language. When we say the universe obeys math, we might be confusing the map with the territory. A map can describe a mountain with great accuracy. It can show elevation, shape, and distance, but the map is not the mountain. It is a representation. In the same way, equations represent relationships in nature. They do not cause those relationships. They only describe them. The Earth does not orbit the Sun because of a formula written in a textbook. The formula exists because the Earth orbits the Sun in a consistent way. We observe regular motion. We translate that regularity into symbols. Math becomes a compressed description of behavior. This idea makes mathematics less mysterious. Of course it works, because we built it to match patterns we observe. We invented numbers to count objects. We developed geometry to measure land. We created calculus to analyze motion and change. Mathematics evolved alongside our need to understand the world. It fits reality because reality shaped it. But this explanation begins to feel incomplete when we look closer. Pure mathematics often develops without any concern for physical application. Mathematicians explore abstract structures for their own sake. They prove theorems about spaces that cannot be visualized. They define objects that seem detached from physical experience. Yet decades or even centuries later, those abstract structures appear at the heart of physics. Non-Euclidean geometry was once a purely theoretical exercise. Mathematicians explored curved spaces without any idea that the universe itself might be curved. Then Einstein used that geometry to describe gravity. Complex numbers were once considered imaginary. They seemed like artificial inventions with no physical meaning. Today they are central to quantum mechanics. Group theory was developed to study symmetry in algebra. It now underlies the standard model of particle physics. These are not small coincidences. They suggest a deeper connection. If math were only a language shaped by observation, why would abstract branches of mathematics, developed without reference to the physical world, later describe it so precisely? Why does the universe align with structures discovered purely in thought? The mystery deepens when we ask a more basic question. Why are there patterns at all? Why does the universe behave consistently? Why does gravity follow an inverse square law everywhere we measure it? Why does light always travel at the same speed in a vacuum? Why do the laws of physics appear uniform across billions of light years? Chaos is possible in principle. A universe where physical constants change randomly from moment to moment is imaginable. A universe where cause and effect break down is logically conceivable. Yet the universe we observe is deeply ordered. It is governed by symmetry. Symmetry means certain properties remain unchanged under transformation. Rotate a circle, and it looks the same. Shift an experiment in time, and the laws do not change. Move a laboratory to another location, and the equations still hold. These symmetries lead directly to conservation laws. Conservation of energy. conservation of momentum, conservation of charge. Mathematics captures these symmetries with precision, but the existence of symmetry itself is not explained by math. It is simply observed. Why should symmetry exist? Why should simple laws generate immense complexity? From a handful of equations describing fundamental forces, we get stars, planets, chemistry, life, and consciousness. The same equations govern all of it. This layering of complexity on top of simple rules is one of the most astonishing features of reality. Mathematics does not just describe isolated facts. It reveals deep unity. The same mathematical structures appear across different domains: waves in the ocean, sound waves in air, light waves in space, and probability waves in quantum mechanics share similar equations. Patterns repeat at different scales. Fractals appear in coastlines, snowflakes, and branching trees. The Fibonacci sequence appears in flowers and galaxies. Order echoes through nature, and then there is the question of the human mind. Why can we understand this structure at all? The brain is a biological organ shaped by evolution. It evolved to survive on the savannah, not to solve tensor equations. Yet it can grasp abstract mathematics that describes black holes and quantum fields. Why should the mind be capable of uncovering the deep structure of the cosmos? This is where the phrase unreasonable effectiveness of mathematics becomes powerful. It captures a sense of surprise. Mathematics is not just useful, it is extraordinarily effective, unreasonably so. Its success seems out of proportion to what we would expect from a human invention. If math were only a convenient shorthand, we might expect rough approximations. Instead, we find exact predictions, measured to many decimal places. The precession of Mercury's orbit matches general relativity with stunning precision. The magnetic moment of the electron matches quantum electrodynamics to an accuracy of more than 10 decimal places. These are not vague correspondences. They are exact fits between abstract equations and physical measurements. The more we examine the universe, the more mathematical it appears. Space and time merge into a geometric structure. Particles become excitations of fields defined by equations. Information becomes a fundamental quantity. Some physicists even suggest that at the deepest level, reality may consist not of matter, but of mathematical relationships. In that view, what we call physical objects are patterns in an underlying mathematical structure. Yet even this bold idea does not remove the mystery, it only shifts it. If reality is mathematical, why does mathematical structure exist? If math is discovered rather than invented, where does it reside? Does it exist independently of minds? Is it timeless and abstract, waiting to be uncovered? Or is it inseparable from physical reality? Each answer opens new questions. The strange power of mathematics does not fade under examination. It grows. Every successful prediction adds to the puzzle. Every elegant equation deepens the sense that something profound connects logic and existence. The universe does not appear random. It appears structured in a way that mathematics can capture with precision. Whether math is the language of the universe or the fabric of the universe remains unsettled. But the effectiveness of math forces us to confront a deeper mystery. Why is reality intelligible? Why is it ordered? Why is it accessible to reason? And why does the abstract realm of numbers align so perfectly with the concrete realm of matter and energy? The question is no longer just about equations, it is about the nature of existence itself. At this point, the question splits into three powerful explanations, and each one changes how we see reality. The first explanation says, mathematics is something we invented. It did not exist in the stars or in empty space before minds appeared. It began with human observation. Early humans counted animals, measured land, tracked seasons, and noticed repeating cycles. Numbers were created to keep track of objects. Geometry was created to measure distance and shape. Algebra was developed to solve practical problems. Calculus was invented to understand motion and change. Step by step, mathematics grew from human needs. In this view, math fits the universe because we shaped it to fit. We observed patterns in nature. then built symbolic systems to describe those patterns. If something did not fit, we adjusted the math. Of course it works, because it was designed to match what we see. When a tailor makes a suit for a person, the suit fits because it was measured and shaped for that body. In the same way, mathematics fits reality because it was cut and shaped by reality. This explanation feels simple and grounded. It removes the mystery. There is no magic connection between mind and cosmos. There is only careful observation and refinement. If a certain branch of math does not match physical reality, it remains abstract and unused. Only the parts that match survive in science. But even this explanation has cracks. Much of mathematics was developed without any connection to physical observation. Mathematicians explored prime numbers, abstract spaces, imaginary numbers, and higher dimensions without knowing whether any of it described the real world. Yet again and again, these abstract creations later became essential in physics. It is difficult to say we invented those structures just to fit nature when they were developed long before anyone knew they would fit. The second explanation takes a very different position. It says we do not invent mathematics, we discover it. Mathematical truths seem independent of human minds. The ratio of a circle's circumference to its diameter is pi, whether anyone calculates it or not. The fact that there are infinitely many prime numbers does not depend on culture or language. 2 plus 2 equals 4 in every possible civilization. These truths feel objective. They feel timeless. In this view, mathematics exists in a realm of abstract reality. Humans uncover it slowly, like explorers mapping a continent that was always there. When mathematicians prove a theorem, they are not creating truth, they are revealing it. If intelligent beings existed elsewhere in the universe, they would likely discover the same mathematical truths. They might use different symbols, but the relationships would be identical. That suggests math is not a human invention, but a fundamental feature of reality itself. If this is true, then the success of mathematics in physics is less surprising. The universe behaves mathematically because mathematical structure is built into its fabric. We are discovering the code that already governs existence, but this explanation raises new questions. Where does mathematics exist if not in human minds? Does it exist in a separate abstract realm? How can physical beings access non-physical truths? What connects the realm of numbers to the realm of matter? The third explanation goes even further. It says the universe is not just described by mathematics, it is mathematics. This is a radical idea. It suggests that physical reality is nothing more than a mathematical structure. In this view, particles are not tiny solid objects. They are excitations of fields defined by equations. Space and time are not backgrounds where events happen. They are geometric relationships within a mathematical framework. Even matter reduces to patterns of information. When physicists describe an electron, they do not describe a small hard ball. They describe properties like charge, mass, and spin, which are values in equations. The deeper science goes, the less physical things seem, and the more mathematical they become. If this view is correct, we are inside an equation. The universe is a vast mathematical object, and we are self-aware substructures within it. Reality is not made of substance, but of relationships. Information replaces matter as the fundamental ingredient. This idea sounds extreme, yet modern physics already points in that direction. Quantum mechanics describes reality in terms of wave functions, probability amplitudes, and operators in abstract spaces. General relativity describes gravity as geometry. The standard model of particle physics is built from symmetry groups and field equations. The language is entirely mathematical. Some physicists argue that once you remove the equations, nothing remains. There is no extra layer underneath. The equations are the reality. If that is true, then asking why the universe obeys math is like asking why a triangle obeys geometry. It does not obey geometry, it is geometry. But even this bold idea does not remove every mystery. Why does this particular mathematical structure exist instead of another? Why are the constants of nature set to these values and not others? Why does a mathematical structure give rise to conscious observers who can reflect on it? The puzzle shifts but does not disappear. At this stage, it helps to step back and consider a more grounded perspective, one that avoids grand metaphysical claims. Richard Feynman offered such a view. He did not speak about abstract realms or cosmic equations. He focused on what science actually does. Nature behaves in certain ways. Scientists observe that behavior. They create mathematical models to describe it. If the model matches experiment, it survives. If it does not, it is rejected. For Feynman, the key principle was simple. The test of any mathematical law is experiment. If math disagrees with experiment, math is wrong. Nature is always right. This perspective removes the need for deep metaphysical speculation. It treats mathematics as a tool, a powerful tool, but still a tool. The question is not why the universe obeys math. The question is whether the mathematical description works. Science does not claim to explain why the laws of nature exist. It only seeks to describe them accurately. Feynman often warned against asking why in a way that demands ultimate explanations. He believed that at some point, explanations reach a foundation. We can describe how things behave, but asking why at a deeper level may not lead to meaningful answers. For example, we can explain gravity as the curvature of space-time, but if someone asks why space-time curves in response to mass, the answer eventually reaches the structure of the equations themselves. Beyond that, there may be no further explanation. From this practical standpoint, the success of mathematics is not mystical, it is empirical. We try equations, we test them, we refine them. Over time, the ones that survive are those that match reality with high precision. There is no guarantee that math will always work. It works because it has worked so far. The moment it fails, scientists search for a better description. This approach avoids claiming that math exists in a separate realm. It also avoids claiming that the universe is literally made of math. It focuses on usefulness. Does the equation predict outcomes? Does it match observation? Can it be tested? If yes, it becomes part of physics. If no, it is discarded. Yet even this practical view does not fully erase the sense of wonder. Why should mathematics be such an effective tool in the first place? Why should the universe behave in stable, repeatable patterns that can be captured by symbols? Why should experiments yield consistent results across time and space? Feynman might say that is simply the way nature is. There is no deeper reason available to us. The laws of physics are the way they are. Our task is to discover them, not to explain why they exist at the deepest level. In this sense, the real question shifts. Instead of asking why the universe obeys math, we ask whether mathematics provides the most accurate and efficient description of observed patterns. So far, it does. It compresses vast amounts of information into compact formulas. It reveals hidden connections between phenomena. It predicts outcomes with extraordinary precision. That is enough for science. The metaphysical interpretation can remain open. Some will prefer the view that we invented math as a refined language shaped by experience. Others will argue that mathematical truths are discovered and exist independently of us. Still others will embrace the idea that reality itself is a mathematical structure. The debate continues because each perspective captures part of the truth, yet leaves open questions. The invention view explains the adaptability of math, but struggles with its predictive power in abstract cases. The discovery view explains objectivity, but raises questions about the existence of abstract entities. The mathematical universe view explains the deep alignment between equations and reality, but leads to further questions about why this structure exists. Meanwhile, the practical scientific approach continues without waiting for final philosophical answers. Equations are tested, predictions are made, experiments are performed, the cycle continues. Nature behaves, mathematics describes. When description and behavior align, science advances. When they do not, models are revised. This ongoing process does not require certainty about whether math is invented or discovered. It only requires careful measurement and logical reasoning, and yet beneath the practical surface, the deeper mystery remains present. Every time an equation predicts a new particle or a new cosmic phenomenon before it is observed, the question returns: why should symbols on paper correspond so precisely to events in the universe? Why should logic developed in human thought map onto the structure of reality? The three explanations offer different lenses, but none completely dissolve the sense of wonder. Perhaps that tension is unavoidable. Mathematics stands at the boundary between mind and world. It is abstract, yet effective. It is logical, yet descriptive. It is invented in one sense and discovered in another. It is a tool and possibly the fabric of existence. Feynman's grounded attitude reminds us to stay anchored in experiment. Grand claims must face empirical testing. Theories must produce measurable predictions. The ultimate measure is not philosophical elegance, but agreement with observation. In that sense, the success of mathematics is judged not by metaphysical certainty, but by experimental confirmation. The equations survive because nature allows them to survive. Whether that survival reflects deep identity between math and reality, or simply the power of human pattern recognition, remains open. The exploration continues, driven by curiosity, guided by logic, and tested by experiment, as the strange partnership between mathematics and the universe unfolds further without final closure. After everything we have explored, the mystery does not disappear. It becomes sharper. Maybe math works because the universe is structured, not slightly structured, deeply structured. From the smallest particle to the largest galaxy cluster, reality follows consistent patterns. Energy behaves in stable ways. Space has geometry. Time has direction. Forces follow precise relationships. If the universe were not structured, nothing could last. No atoms, no stars, no life. Structure may not be an added feature. It may be the only way something can exist at all. A completely chaotic universe would erase itself instantly. No stability, no memory, no observers. Order might not be special, it might be necessary. But even that idea opens another door. If structure is necessary for existence, then mathematics may simply be the language of structure. Wherever there is pattern, there is number. Wherever there is symmetry, there is geometry. Wherever there is change, there is calculus. In that sense, math does not control reality. It reflects the deep regularity that allows reality to hold together. Or maybe we are asking the wrong question. When we say, why does the universe obey math? We assume math and the universe are separate things. We assume one follows the other. But what if that separation is artificial? What if mathematics is not outside reality looking in? What if it is woven into the fabric of existence itself? In that case, asking why the universe obeys math would be like asking why a circle obeys the rules of geometry. It does not obey them, it expresses them. Now push the question further. What would a non-mathematical universe even look like? A universe where 2 plus 2 sometimes equals 4, and sometimes equals 5. A universe where gravity works on Monday, but fails on Tuesday. A universe where symmetry breaks without reason, where patterns do not repeat, where cause does not lead to effect. Such a universe would be impossible to understand, would be impossible to survive in. It might even be impossible to exist in a stable form. The very act of existing may require consistency, and consistency is mathematical at its core. So maybe the real mystery is not that math works. Maybe the mystery is that anything exists at all. And if something exists, perhaps it must exist in a structured way. And if it is structured, mathematics is unavoidable. Still, one question remains quietly in the background. Why this structure? Why these laws? Why this elegant balance of symmetry and complexity? Science continues to search. Equations grow deeper. Experiments grow more precise. Yet the foundation remains silent. Maybe the universe doesn't obey math. Maybe math is the shadow of something deeper. If this question made you pause, if it changed the way you see numbers, physics, or even reality itself, then this journey was worth it. There are many more mysteries waiting to be explored. Like this video so more people can discover it. Share it with someone who loves deep questions, and subscribe to our channel to join us as we continue exploring the hidden structure of the universe, one idea at a time.